This video will take a look at what's called the reaction quotient. To start our discussion, let's go back to an equilibrium between hydrogen and iodide, making hydrogen iodide. The green line here representing the product, hydrogen iodide. To evaluate the equilibrium law expression, we require knowledge of the concentrations at equilibrium. So anything to the right of this dotted line, we would be evaluating the equilibrium constant. So taking those concentrations and putting them in the expression, we'd come up with a number for the equilibrium constant. The reaction quotient is evaluated in non-equilibrium conditions. So that would perhaps be over here at this side, to the left of the line. We haven't reached equilibrium yet. We still use the equilibrium law expression. However, we use the concentrations that are present in that region. That'll give us, in this case, a value that's actually smaller than the equilibrium constant. Evaluating Q lets one determine if one is at equilibrium, and if not, what direction the reaction needs to proceed, either forward or reverse. Let's look at an example. To form ammonia from nitrogen and hydrogen at 500 degrees K, the equilibrium constant is around 170. We've been given here some concentrations that were measured. The question is, are we at equilibrium? Well, let's start by determining then what Q would be, since we're not sure we're at equilibrium. We substitute in the values that were given for the ammonia, the nitrogen, and the hydrogen, and we come up with a number. That's called the reaction quotient. We can then compare that to 170. Since we're not equal to 170, we're not at equilibrium. And the fact that we're less than 170 tells us that in order for the reaction to approach 170, we need to proceed in the forward direction to produce more product. So that's a quick look at what the reaction quotient represents.